19.3 times of H2O, which I'm just going to list as 1, right? Because the density of water we list as 1 gram per cubic centimeter, or it's 1,000 kilograms per cubic meter. But in terms of specific gravity, we list the density of water as 1, because specific gravity is the density of the object divided by the density of water. So for those who have had chemistry, you have that. If you've not, I'm pretty sure you got something of that back in life sciences and dealt with that, right? And then G is 0.96 of water. So what is gold to her? What is the ratio of her density, or gold's density, to her density? You're going to take your 19.3 and divide by 0.96 and get 20 something. Okay? So now we read the rest of the problem. That's the first thing, is just to get what's happening on that part of it. If the statue of Barbara is made out of gold in the exact proportions of Barbara's measurements and weighing exactly what Barbara weighs, how tall will the statue be? So, the mass is the same, because weight and mass are just a multiplier of 9.8 difference between them. All right? We're going to find out that, think about this, if the statue was exactly her size, right, it would have 20 times the mass. Right? So, would I take 1/20th the height? Would I take 1/20th the size so that I'll get the same mass? Well, what is mass proportional to? If I take something that is twice as large, does it have twice the mass? Same proportions, we get something, right? If I have some mass, right, it's proportional, and I'll give you a hint here, it's proportional to volume. Yes. Right? If I double the volume, okay, I'm going to double the mass. Not a problem. That's the concept of that. But volume is going to be length cubed. Right? Height times width times length. So if I double length, I have 8 times the mass. You follow? All right. If I have 20 times the density, I need the cube root of 20 as a factor of length change. Because don't I need 1/20th the volume? Her gold statue has to be 1/20th of her volume, so that the mass, or the weight of the statue and the weight of her are the same. Since I have a 20-something density change. That makes sense for everybody? All right. So we're going to take the 100. How tall is she? 162.6.
Yeah.
Okay. So it's 162.6 centimeters, and I want to divide by the cube root of whatever that value was. All right. Now I'm going to also assume. Oh, they didn't even do that one, did they? If I just divided by 20. 6 or 7. 8. Well, they were nice. They didn't give you the 162.6 divided by 20 value as one of the options. If I was writing this test, I would have given you that as an option. So that's because I'm mean and cruel. You know. All right. What's that, like 2.5? That's right. The cube root of 20 is around 2.5.
Yeah.
So
Because 3 is
27.
So we've got half a little more than
and that's, so it's around 60. The guess ought to be 59.8 because that's the closest to 60. I don't have my answers here. All right, boxes of masses moved. How much work is required to move distance? Anytime you see, there are two words that end the first sentence. What are the two words that end the first sentence? Constant speed. That tells you something. Constant speed in a straight line communicates then that the net force is 0. All right? So what do I have? I have a box being pulled along the floor. I'm applying a force. If my box is going at a constant speed in a straight line, it's not accelerating. That means the net force is going to be 0. So I have weight going down, I have force normal going up, and I better have something pulling back that way, which would probably be the force of friction. All right? Since it's a nice horizontal force, where I'm not worried about all those other things, right? All right, so my force of friction is mu times force normal, so that's going to be mu times mg. And since these two forces are equal, work is force dotted into displacement. A review for some of you, for those that are not, let me give an understanding for the dot product. All right? And I'll tell this story to my classes, so some of you have heard it or not. But I'm going to pick on Rishi. Rishi's going to go off to college, right? Her parents are going to be so excited. They're going to take all of her stuff to whatever college, whatever dorm room it is. They're going to throw it out of the car, dump it onto the sidewalk, and just take off because they're going to go on a cruise because Rishi's off to college. Yay! All right, so Rishi starts moving in all of her boxes and all of her stuff. But one of the things that she has all of the stuff that she's taking into her dorm room is going to be a couch. Okay, and so here we have this couch, right, and it's the ground, and we need to get it into the dorm room. All right, well, if we think about the couch, we do a free body diagram, of course. There's the weight of the couch going down, the ground's pushing up. All right, and you do understand that the weight of the couch going down and the ground pushing up adds a 0, right? Because the couch is not accelerating through the ground. All right, and nor is the ground pushing the couch up into the air. All right, now is Rishi going to move the couch into her dorm room? Of course not. What is Rishi going to do? It's going to smile at some guys and ask the guys to do it, and the guys are going to fall all over themselves and they're going to carry the couch in because that's what girls do. Okay, yes, it is there. Okay, gentlemen, please understand, you have already lost this battle. Don't even fight it. Don't even try to fight it. Just move the damn couch. Okay? It's what you need to do. I know I'm on video, but I don't care. It's 3:15. School's over. Yeah, I don't want to get in trouble, so I don't care. Right? Please, if you are offended, I apologize. But as far as things go, gentlemen, just be a gentleman and move the couch. So what we're going to do here is we are going to get one guy pulling on the couch that way, one guy pulling and pushing on the couch that way, and Rishi's going to sit on the couch here, motivating them. Okay? Now, remember here, work is F dot D. I apply a force, move through a distance, I'm going to be doing work. Is Rishi applying a force to the couch? Absolutely. Gravity, right? So we slide the couch over, we get it into the dorm room. Has Rishi done any work in moving? She applied a force, the couch went through a distance. Has Rishi done any work in moving the couch? No. Okay? Because what happens here is work, or we do this as the absolute value or the magnitude of that work. I'm not going to do absolute value because I can get a negative here. Is going to be the magnitude of the force, the magnitude of the displacement, times the cosine of the angle between them. Now, first thing I want to deal with on this When you add vectors, how do you add them? You draw one vector, draw the picture. So you graphically, I want to know, how do you add vectors graphically? Head to tail addition. You draw the first one, you put the second one on the head of that, draw that one, and you can add as many vectors as you want. All right? When you are looking for the angle between two vectors, you put the tails together. All right? And it's like the only time you ever put the tails together. But the angle between vectors, you put the tails together, that solves for what that my theta is here. All right. So for this person pulling, moving in that distance, what's the angle between the two vectors? 0. What is the cosine of 0? 1. And so that person does positive work. Force of friction, because they were sliding it on the ground. Right? Force of friction would be this way. My displacement was that way. What's the angle between the two vectors? 180. What's the cosine of 180? Negative. And it's -1, right? Friction does negative work. We good? Okay. Does that make it a vector?
Does it make the work effective?
Does it make work a vector because I had one that was positive and one that was negative? No. Okay. Can you is money a scalar or a vector? It's a scalar, right? I can't have $12 north, right? And that's different than $12 south. Matter of fact, if I added $12 north and $12 south, you would get no dollars at all if it was a vector. But if you have $12 north and $12 south, you got $24 because the direction doesn't matter, right? But is it adding money to your bank account and subtracting money from your bank account the same thing? No. So a scalar has a plus or minus to it. Make sure that those work and you have that one. So I have FD cosine theta. What is the angle between Rishi's force and the movement of the couch?
90 degrees.
90 degrees. What's the cosine of 90? 0. Therefore, Rishi does no work. Okay. Does the sun apply a force to the earth?
Yes. No.
Don't listen to Jeff. Does the sun apply a force to the earth? Absolutely. And in physics land, what is the shape of the orbit of the earth about the sun?
Circle.
Completely circle.
It's a circle.
Circle.
Okay? In real land, what shape is it?
Ellipse.
It is an ellipse. All right? The planets that go, for our planets all circling the sun, most of them are really, really nice circles. Mars was enough of an ellipse that they could actually make and track that difference. All right? A man named Kepler came up with Kepler's 3 laws, one of which is, the first one is that the planets move in elliptical orbits. All right? His ability to prove that, if you think about this, is kind of an amazing thing. All right? He took somebody else's data, and that was he was able to plot where Mars was on any given night over the period of like 4 years. From knowing where Mars was relative to Earth on any given night, he was able to make a 2-dimensional, basically, graph of, or a plot of where Mars was around the sun. And from that understanding, tried to draw a circle, and the circle didn't fit. All right? And so that's why I come up with, oh, well, if we make it an ellipse, everybody's happy. Except for the theists, because it was just wrong. But they were wrong, and so we're okay. All right. Back to the original problem. We are going to the fact that they wanted to know how much work was done. So we've defined work. Everybody good in the understanding for work and moving on? All right, so work is force through a distance. The magnitude of my force that I want to know how much work is done has to be equal to the force of friction. So since my force of friction is mu mg, that's the force applied through the distance. I just multiply the distance, and I get my answer. So we're going to get that 0.246 times 43.7 times 9.8 times 7.13. So 430, 100, 700, and